Hello everyone. Here's the brutal truth about AI agents. 95% of them never make it past the demo stage. You build something amazing in your lab, it works perfectly, answers questions, calls tools, maybe even does a little reasoning. But the moment you push it to production, everything breaks, context vanishes, tools fail, memory gets wiped. Your agent becomes just another dumb chatbot. This is the 12-factor agents framework. It's got nearly 9,000 stars on GitHub and is being used by Y Combinator companies and Fortune 500 teams to build production-grade AI systems. I'm going to show you all 12 factors and exactly how to apply them to your own projects. By the end of this video, you'll have the complete blueprint for building AI agents that actually work in the real world. The first factor is natural language to tool calls, and this is the foundation of everything. Most people think of AI agents as chatbots that can do things, but that's backwards. The real power is in converting natural language into structured actions that your code can actually execute. Let me show you what this looks like. When a user says, create a payment link for 750 to John for the February AI meetup, your agent doesn't just generate text about payments. It converts that request into structured JSON that looks like this. Function name, create payment link, parameters with amount 750, customer ID, product ID, and a memo. This isn't just about tool calling. It's about creating a clear contract between the unpredictable part, which is the LLM, and the predictable part, which is your deterministic code. The LLM decides what action to take, but your code controls how it's executed. This separation is what makes the difference between a demo and a production system. Think of it like this: the LLM is your interpreter, and your tools are your execution engine. The interpreter can be creative and flexible, but the execution engine needs to be rock solid. This pattern alone will solve most of your reliability problems because you're not asking the LLM to do things it's bad at. You're using it for what it's actually good at, which is understanding intent and converting it to structure. Factor 2 is own your prompts, and this is where most people go wrong. They let frameworks generate their prompts automatically, then wonder why their agents are unreliable. Here's the reality: prompts are the primary interface between your application and the LLM. You need full control over every single token. I've seen teams spend months trying to debug agent behavior, only to discover that their framework was injecting random instructions they didn't even know about. Your prompts should be in your codebase, version controlled, and treated like the critical infrastructure they are, not buried inside some black box abstraction. Look at this example. A framework-generated prompt might be verbose and generic, wasting tokens on instructions that don't matter for your specific use case. A handcrafted prompt is dense, specific, and optimized for your exact requirements. The difference in output quality is night and day. This doesn't mean you have to write everything from scratch. Use frameworks to get started, absolutely. But once you need production quality, you're going to end up writing every token by hand anyway. LLMs are pure functions, tokens in, tokens out. The only thing that determines the reliability of your agent is how good your input tokens are. And the only way to optimize those tokens is to own them completely. Factor 3 is own your context window. And this is where context engineering becomes critical. Most systems just use the standard OpenAI message format, but that's incredibly wasteful. You can create custom context structures that are optimized for your specific use case. Here's what I mean. The standard format with separate user and assistant messages is verbose and burns through tokens quickly. But you can create a custom format that's dense, structured, and gives the LLM exactly what it needs to make the next decision. This isn't just about saving money, it's about performance. The context window is your agent's working memory. Everything it knows about the current conversation, the tools available, the user's history, all of that has to fit in that window. If you're not actively managing what goes in there, you're going to hit limits fast. And when you hit those limits, your agent starts forgetting important information. This is context engineering, not just prompt engineering. You're designing the entire information architecture that feeds into your model. That means deciding what to include, what to summarize, what to compress, and what to leave out entirely. Every token in that context window should be there for a reason. If it's not directly relevant to the next decision, it shouldn't be there. The teams that get this right see massive improvements in both performance and cost. They can run longer conversations, handle more complex tasks, and their agents stay focused instead of getting lost in irrelevant details. Factor 4 is tools are just structured outputs, and this is a huge mental shift. Most people think tools are special, but they are not. They are just the LLM outputting JSON that describes what your code should do next. This gives you incredible flexibility in how you handle those tool calls. Let me show you what this looks like in practice. When your agent wants to send an email, it doesn't directly send the email. It outputs a JSON structure that says, I want to call the send email tool with these parameters. Then your code decides what to do with that. Maybe it sends the email immediately. Maybe it queues it for human approval. Maybe it logs it for auditing purposes. This is powerful because it means you can change the behavior of your tools without changing your prompts. A deploy backend tool call might immediately deploy in development, but pause for approval in production. A delete user tool might work normally most of the time, but trigger additional verification if it's a high value account. The key insight is that tools are just structured communication between your LLM and your application logic. The LLM is expressing intent, but your code is making the actual decisions about execution. This separation lets you build complex workflows with safety checks, approval processes, and business logic that would be impossible to implement if tools were just black boxes. Think of it like this. The LLM is your decision maker, but your code is your policy engine. The decision maker can be creative and flexible, but the policy engine enforces your business rules and safety constraints. Factor 5 is Unify execution state and business state, and this is where most agent architectures fall apart. Many systems try to separate these, but that creates unnecessary complexity and makes debugging nearly impossible. Here's the core idea. If you can infer your execution state from your context window, you get one source of truth that's serializable, debuggable, and easy to reason about. Your context window becomes your state machine. Everything the agent has done, everything it's learned, all the tools it's called, that's all stored in the context in a format that both you and the LLM can understand. This is different from traditional software, where you might have separate databases for user data, execution state, and business logic. With agents, it's all unified in the context window. When you need to debug why your agent made a decision, you can look at the exact context it had at that moment. This approach also makes your agent stateless from the perspective of your infrastructure. The agent doesn't maintain internal state between calls. Everything it needs to know is passed in with each request. This makes them much easier to scale horizontally and recover from failures. The practical benefit is that you can pause an agent, serialize its entire state to a database, and then resume it later on a completely different machine. The agent doesn't know or care, it just processes the context and continues where it left off. This is essential for long-running workflows that might take hours or days to complete. Factor 6 is launch pause resume with simple APIs, and this is crucial for production systems. Your agents need to be able to start, stop, and continue exactly where they left off with clean APIs that make this behavior predictable. This is about treating agents like proper software services. You should be able to launch an agent with a simple API call, pause it when it needs human input or encounters a long-running task, and resume it when the external dependency is ready. All of this should be transparent to the agent itself. Let me show you how this works in practice. Your agent is processing a deployment request. It selects the deployment tool, but before executing, it needs human approval. Instead of blocking or timing out, it pauses itself and saves its state to a database. The human gets a notification, approves the deployment, and the agent automatically resumes from exactly where it left off. This pattern is essential for high-stakes operations, where you need human oversight, but you also need the efficiency of automation. The agent can work autonomously for the easy parts, but escalate to humans for the critical decisions. From the user's perspective, it feels like working with a really smart assistant that knows when to ask for help. The technical implementation is straightforward if you followed the previous factors. Your agent state is in the context window, so pausing is just serializing that context and storing it. Resuming is loading the context and continuing the loop. Simple, predictable, and reliable. Factor 7 is contact. humans with tool calls. And this is where the magic happens. Instead of having separate systems for human interaction, you make human contact just another tool that your agent can call. This creates seamless human AI collaboration. The beauty of this approach is that requesting human help looks exactly like calling any other tool. The agent outputs JSON that says, I need human input on these questions with the context and options clearly specified. Your system then routes that request to the appropriate human through whatever channel makes sense: Slack, email, mobile app, whatever. This isn't just about approvals. Your agent can ask for clarification when instructions are ambiguous, request additional context when it's missing information, or escalate issues when something goes wrong, all through the same unified interface. Here's a real example. Your agent is processing a customer support ticket and realizes it needs to access a system it doesn't have permissions for. Instead of failing, it calls the request access tool with the specific system and justification. A human gets notified, grants the access, and the agent continues processing the ticket. The customer experience is seamless, but the security boundaries are maintained. The key is that human interaction becomes part of your agent's natural workflow, not an exception case. This lets you give agents access to higher stakes operations because you know they'll ask for help when they need it. It's like having a smart intern who knows when to escalate to their manager. Factor 8 is own your control flow, and this is where you take back control from the frameworks. Most agent systems use a simple while loop called LLM, execute tool, repeat until done. But production systems need more sophisticated control flow. Different tool calls should trigger different behaviors. Maybe a fetch data call continues the loop immediately, but a delete database call breaks the loop and waits for human approval. Maybe certain tool calls have replay logic while others fail fast. You decide the flow, not the framework. Here's what this looks like in code. Instead of letting a framework control your main loop, you write your own switch statement that handles each tool call type differently. Some continue the loop, some pause execution, some trigger additional workflows. You have complete control over what happens next. This is crucial for error handling too. When a tool call fails, your control flow logic decides whether to retry, escalate to a human, or try a different approach. The LLM can read the error message and adjust its strategy, but your code controls the overall flow and safety limits. The practical benefit is that your agents become predictable and debuggable. You can look at a tool call and know exactly what your system will do next. No more mysterious framework behavior or unexpected infinite loops. Just clear, explicit control flow that you can reason about and modify as needed. Factor 9 is compact errors into context window, and this is what makes your agents self-healing. When things go wrong, and they will, your agent should be able to read the error message and figure out what to change. The key is formatting errors in a way that's helpful to the LLM, not just dumping raw stack traces into the context. A good error message tells the agent what went wrong, why it went wrong, and what it might try differently. Raw technical errors are just noise. Here's an example. Your agent tries to call an API and gets a 401 unauthorized error. Instead of showing the full HTTP response, you format it as API call failed, invalid credentials. Try refreshing the auth token or requesting new permissions. The agent can understand this and take appropriate action. But you need limits, maybe 3 attempts per tool call before escalating to a human. Otherwise, you get infinite loops where the agent keeps trying the same thing over and over. The error handling becomes part of your control flow, retry logic, escalation paths, and circuit breakers. The really powerful part is that agents can learn from patterns and errors. If they keep hitting the same authentication issue, they can proactively refresh tokens before making API calls. If certain operations consistently fail during high traffic periods, they can wait and retry later. This makes your systems more resilient over time. Good error handling can turn your agents from brittle demos into robust production systems. They try something, it fails. They read the error, adjust their approach, and try again, just like a skilled human would do. Factor 10 is small, focused agents, and this is about managing complexity. Instead of building one agent that does everything, build small agents that do one thing well. As context windows grow, LLMs actually get lost and lose focus. Keep your agents focused on 3 town steps, maybe 20 max. This keeps performance high and makes debugging easier. When you have a 50-step agent workflow, it's almost impossible to figure out where things went wrong. But a 5-step agent, you can debug that in minutes. Here's the mental model. Think microservices for AI. Each agent has a single responsibility and a clear interface. Maybe one agent handles research, another handles writing, and a third handles publishing. You chain them together into workflows, but each piece is simple and testable. This approach also makes your system more resilient. If one agent fails, it doesn't bring down the entire workflow. You can fix, replace, or upgrade individual agents without affecting the rest of the system. It's like having a team of specialists instead of one overworked generalist. The practical benefit is that small agents are much more reliable. They stay focused on their task. They don't get confused by irrelevant context, and they're easier to prompt effectively. As LLMs get better, you can gradually expand their scope, but always with quality as the priority, not capability. Factor 11 is triggered from anywhere, meet users where they are. And this is what makes your agents feel like real digital coworkers. Your agent should work across Slack, email, SMS, webhooks, cron jobs, wherever your users are. This isn't just about convenience, it's about adoption. If people have to learn a new interface to use your agent, they probably won't use it. But if it works in tools they already use every day, it becomes part of their natural workflow. The technical implementation is straightforward if you follow the previous factors. Your agents are stateless and communicate through tool calls, so they can be triggered from any channel and respond through the same channel. A Slack message, an email, a webhook, they all just become different ways to launch the same underlying agent. This enables what I call outer loop agents. Agents that can work for hours or days, get triggered by external events, and contact humans when they need help. Maybe an agent monitors your deployment pipeline and automatically creates tickets when builds fail. Maybe it processes support emails overnight and escalates complex issues to humans during business hours. The key insight is that agents become more valuable when they integrate seamlessly with existing workflows. They're not replacing human tools, they're becoming smart extensions of those tools. This is how you get from AI experiments to AI systems that people actually depend on. Factor 12 is make your agent a stateless reducer, and this is the functional programming approach to agents. Your agent takes the current state and an event and produces the next state. No internal memory, no hidden state, everything is explicit and predictable. This is a profound shift from traditional software architecture. Instead of objects with internal state, you have pure functions that transform inputs into outputs. The agent doesn't remember anything between calls. Everything it needs to know is passed in with each request. Here's what this looks like in practice. Your agent function takes a context window and an event and returns a new context window plus any actions to take. It's completely stateless from the perspective of your infrastructure. You can run the same agent on different machines, pause and resume it anywhere, and scale it horizontally without worrying about state synchronization. This approach makes your agents incredibly robust. There's no hidden state to get corrupted, no memory leaks to worry about, and no complex initialization procedures. Each call is completely independent, which makes debugging and testing much easier. The practical benefit is that stateless agents are much easier to scale and deploy. You can run them in containers, serverless functions, or traditional servers without changing anything. They are also easier to reason about because there is no implicit state. Everything is explicit in the function signature. This is the foundation that makes all the other factors possible. Stateless agents can be paused and resumed. They can be triggered from anywhere, and they can handle errors gracefully because there's no internal state to corrupt. So there you have it, the complete 12-factor agents framework. These aren't just theoretical principles, they are battle-tested patterns that teams are using right now to build AI systems that actually work in production. The key insight is that production AI agents aren't just about having the smartest model, they're about having the right architecture. Start with factors 1 3, own your prompts, context, and tool calls. Those alone will dramatically improve your agent's reliability. Then gradually add the other factors as you scale. Remember, agents are just software. The teams that succeed with them understand this and apply solid engineering principles. They don't chase the latest framework or the newest model, they focus on building systems that are reliable, maintainable, and scalable. I've linked the GitHub repository in the description. It's got detailed examples for each factor and is actively maintained by the community. If you're building AI agents, this is required reading. And if you found this helpful, make sure to subscribe because I'm covering more advanced AI architecture patterns in upcoming videos. The future of AI isn't about replacing humans. It's about building systems that make humans more productive. The two-factor agents framework gives you the tools to build those systems. Now, go build something amazing.